One thing about numbers we didn't get to on Tuesday, scientific notation. Y'all used this before? Some people kind of have this look like yes, yeah. Yes, right. So scientific notation, what does it look like? How would you describe it to somebody? Yeah, exponents. And what's the point of it?
To save you space.
To save you space, and that's actually part of it. That yeah, really big, really small numbers take a lot of space to write down, and so you can write it down in a smaller space. There's actually a more important reason to use scientific notation related to what we talked about on Tuesday, and that is this issue of measurement precision. So let me give you an example. Let's say we write the number 1,000. All right, we measured something and it was 1,000 meters or something. Okay. This is a fine number, nothing wrong with that number, but it doesn't tell us about the precision really. It doesn't tell us, is this exactly 1,000? Is this between 99 or 999 and 1,001? Or is this between 900 and 1,100? Where is that uncertainty? Which is our uncertain digit? Is it this one, is it this one, or is it this one? There's no way of knowing that when you just write 1,000 like this. And so what we can do instead is we can convert this into scientific notation where it is clear. So how would we convert 1,000 into scientific notation? Anybody know? Have you done this before?
Remove the zeros.
Yeah, you move the zeros around. So what we do is we take the decimal place where it is right now. Whoops, I don't need help. Wrong button. We take the decimal place where it is now, which is right there, and we move it over to the left until there's only one number left on the left. We count the number of times we move it. So we go 1, 2, 3. Now there's one number left on the left. All right? And so this becomes 1 times 10 to the third because we moved it 3 times. But there's a couple different ways we can write this. It can be 1 times 10 to the third. It could be 1.0 times 10 to the third. Could be 1.00 times 10 to the third. Or it could be 1.000 times 10 to the third. Those are all ways of writing 1,000. What's the difference in them? What's the difference among those 4 ways of writing 1,000? The what?
No.
Yeah, the decimal is actually always in the same place. It's always next to the 1. Yeah, it changes the significant figures. It changes the precision. So this first way of writing it has 1 significant figure, and this tells us that this must be the uncertain digit. So that means that this is between 0.9 times 10 to the third and it's between 0 times 10 to the third and 2 times 10 to the third. So a huge range, right? That's 100, or wait. There's 100. There's a big difference between those. It's hard to even talk about it. This one now is between 0.9 and 1.1 times 10 to the third. This one, which is another way of saying 900 and 1,100. This one, the difference is 990 to 1,010, and this one is the most precise, so that's going to be a range of 999 to 1,001. Now, which one's correct? Well, that depends on your experiment and what you're actually measuring and how many significant figures you need. But the point is that without scientific notation, you can't express that. There's no way to express these different levels of precision when we just write 1,000. So beyond just making it easier to write big and small numbers, scientific notation helps us to clarify our level of precision based on our measurement. So let's practice this a little bit. Let's look at some different numbers in scientific notation. $12,430. How would I write that in scientific notation? See if you can do the same procedure that we just did. Move that decimal place over, count as many times as you can, and write down what you think is 12,430 in scientific notation. kind of give you a minute. When I see pencils stop moving, I'll continue. All right. What'd you come up with? Anybody want to volunteer?
I have
1.2 times 10 to the fourth. Okay. So to get something different? Yeah. Oh, go ahead.
I left them, I just put 1.243 times.
Okay. Anything else? Did you have the same? Yeah. Okay. Did anybody get something different? Did anybody get something wildly different? No? Yeah. Like that? Okay. Okay. Anything else? All right, let's look at some of these different ones. So the first two are pretty similar except for the number of significant figures that were left on. They're both correct in terms of expressing this number in significant figures, and it just depends on the precision. My general rule to you, again, it depends on what you're measuring, but if you're converting a number from regular decimal notation to scientific notation, it's best to not round it off. Leave all the significant figures there, because you may not know exactly what the precision should be. So calling this 1.243 or 1.2430 is fine. So those would be good. These two, these are technically correct in terms of, or in the way that they also express that number. So 12.430 times 10 to the third is the same as 1.243 times 10 to the fourth, if the exponent just changes, as is 1243 times 10. The problem with those is they violate the convention of scientific notation, which is that you only leave one digit to the left of the decimal place. So it's not that they're wrong. They are also ways of expressing this number, but they're not technically scientific notation when they have more than one number to the left of the decimal place. So we're going to stick with that one number to the left of the decimal place rule. Yeah.
So, I don't know, can you, is this helpful to take into account 1.243 0.0000 times 10 to the fourth?
Sure, in this case, but we don't know how many zeros we could put on there because it'll depend on our actual precision of measurement. But yeah. Because depending on how precise this one is, I guess in that case you can't be more your scientific notation can't be more precise than your original number. So you can't really have more than 5 significant figures here.
Right, you convert whatever you see in front of you as opposed to adding on.
Right, unless you have a good reason to do so. Yeah.
But you wanted to leave the 4-3 on there, right? So
Yes.
The second one would be the best answer?
Yes, I think so. Again, depending on your precision in your instrument. But if you just see this number and you want to convert it, best to leave the other stuff there with it. All right, let's go the other way. .36 times 10 to the 6th. Write that out in standard notation. What would that look like, and how do you do that? So here we're doing the reverse. What'd you come up with? What? Like that? Okay. Anybody get something different? Looks good? Okay, great. Like you got a good sense of this. So the way I would do this if you want a specific procedure is I would write down the numbers that I'm giving, the significant figures, and then I would start counting the 6 places away. So kind of the reverse count from what we did before. So I'd start here and go 1, 2, 3, 4, 5, 6, and then add zeros to those extra little spots that we made. And then you can rewrite the number and make it look nice. But that way you're sure to get the right number of zeros. And then we can also do this for very small numbers, but instead of multiplying by 10 to some power, we want to divide by 10 to some power. And how do we express that? You know? How do we express dividing by like 10 to the third rather than multiplying by 10 to the third? We don't use a division sign, we use something else. You know? What? It will be a fraction, but the notation we use for that is a negative exponent. So if we have the number like this, in order to make that into scientific notation, again, we want just one digit to the left of the decimal place. So that means 1, 2, 3, 4, 5, 6 moves. And this number is going to be 1.23 times 10 to the negative 6, because we're making a small number. Right. A negative exponent means divide by that. So that means 1 over 10 to the 6th. That's where that comes from. We see these a lot in chemistry because we work with these types of quantities. We often work with very large numbers of things because molecules are so small. We work with very small things because, again, molecules are so small. So when we talk about individual properties of atoms and molecules, like masses and charges, those tend to be really small numbers. And we really need scientific notation, or we're just writing zeros and zeros and zeros all the time, and it's hard to know. The other issue then is with our precision. So if this is something that you haven't thought about in a while, probably makes sense to review it, practice it a little bit. You'll see some practice in your book for these. Any questions about that? All right, let's move on and talk about some units. So there are some metric prefixes that you should know. Definitely both for this class, but for the rest of everything you do, especially if you're going into health sciences. Most drugs and other types of medications, intravenous fluids, all this kind of stuff are all measured out in the metric system. And so you need to have a decent facility with that. So what is the metric unit of length? You know? Meters, yep. And what is the unit of mass? The gram or kilogram. What about temperature? Yeah, degrees Celsius or Kelvin, which we'll talk about in the next chapter. And then volume? Liter. Yeah. Okay, you should know those, or you should learn those and know them for stuff we do in this class. And then you also need to know some prefixes as to how they relate to the original. So if a meter is a particular length, what is a kilometer or kilometer? How many meters is that? Yeah. So a kilometer is 1,000 meters. And in general, a kilo of anything is going to be 1,000. So a kilogram is 1,000 grams, and so on. Okay. Other prefixes you should know. C or centi, like centimeter. is a 100th. So there are 100 centimeters in a meter. And then milli is a 1,000th. So there are 1,000 millimeters in a meter, 1,000 milligrams in a gram, 1,000 milliliters in a liter, and so on. If you get confused about which things you need to know or not know, if you jump back to Blackboard, in the measurements section here, you see under the chapter objectives which ones you need to know. So you need to know the meaning of the prefixes kilo, centi, and milli, but other conversions that we'll talk about in a little bit, like going between metric and English units, I'll give you those numbers. So you need to know how to use the numbers, but you don't need to memorize the numbers. And if you ever get confused on that, you can go back to those objectives, and that'll always be clear what you need to know and what you don't. So let's practice this a little bit and talk about how we can convert from one to another. So let's say a patient needs 0.024 grams of a sulfa drug. How many 8 milligram tablets should be given? Right. So you've got your dose in grams, but you have your tablets in milligrams. What we need to do is put those numbers in the same units so they can be more clearly compared. So we either need to convert the 0.024 grams to milligrams or the 8 milligrams to grams so that we can compare these more closely. What is a sulfa drug, by the way? Do we know? What kind of a medicine is that? So what? It's not a painkiller, but I guess related. It's a type of an antibiotic. It's a class of antibiotics. It's not. There are several that are used, especially topical creams now. There are a lot of people that are allergic to them, so they're not as generally used as something like the penicillins, but they have their place. So this kind of a thing is something that will come up a lot in medicine. And when I talk to nursing faculty, people who teach in health sciences, and ask them about what kind of things we should really focus on, this is the kind of thing that always comes up. They talk about how they really wish people had a better, stronger sense of how to convert from one unit to another. It comes up all the time in medicine because different medicines are given in different amounts. There are all kinds of weird units that are in use in pharmacies. There's metric units, there's English units, there's weird old-fashioned pharmacy units that nobody else uses that sometimes come up. Some medications are just dosed in their own units. It's just units. That's not a particular measurement. So you always have to have a good sense of how these things interrelate and how to convert them. And as someone working with patients, it's always good to be able to provide a check to these conversions, because maybe the pharmacist or the doctor is doing these conversions initially, but you need to be able to check that and make sure that it's correct. So let's work this out. So what do we need to do to turn this number of 0.024 grams into milligrams? How do you figure that? How do you know that?
What I have it set up in my head is that you put 1/1,000 times 0.024 grams. Therefore, not enough grams because there's not enough grams.
Okay. Okay. Yeah. So let's set this up. And again, if you have a lot of experience with this, you may kind of have your own little system of how to do these. That's fine. Just ignore what I'm saying. Use whatever works for you. But this is the way that I found, and that I found works well, and that a lot of other people have liked as well. We use something called an identity, which means that we use the fact that there are 1,000 milligrams in 1 gram, that those are really equal to each other. Those are equal quantities. Which means that if we make a fraction out of this, like 1 gram over 1,000 milligrams, or 1,000 milligrams over 1 gram, we're dividing two things that are the same, which is just 1. It's like multiplying by 1. So we can always multiply by a factor that is equal to 1, and therefore we can multiply by something that is the same thing on top of another same thing. The reason this is useful, though, is because the units are different. So let me show you what happens. We can take our number here, 0.024 grams, and what we want to do is multiply it by a factor that allows grams to be divided by grams and therefore cancels out and leaves milligrams. The way we do that is by putting the grams on the bottom and the milligrams on the top. This number by itself is assumed to be on the top, so we would say grams divided by grams means that the grams will cancel out, and we're left with milligrams. All that's left then is to fill in the conversion numbers from our original conversion. So the 1,000 goes with the milligrams, and the 1 goes with the grams. To solve the problem then, you multiply through by everything on top, and you divide by anything on the bottom. So this would be solved by saying 0.024 times 1,000 divided by 1. We don't need to put in the divide by 1. And that leaves us with 24 milligrams. Now we have a clear comparison with the tablets. So if we have 8 milligram tablets and we need 24 milligrams total, how many tablets do we need to give? 3, because it's clearly, or we divide here 24 divided by 8, that means 3, or that results in 3. So 3 tablets give us that particular dose, and we did the conversion to go to the same units. Sound good so far? Okay, now let's look at what happens when we have to switch units. So let's say the same patient, before they figured out their dose, they came into the doctor and the doctor said, well, how much do you weigh? Or they put him up on the scale, and it said about 155 pounds. But on that dosing chart, it talks about milligrams per kilogram. So we need to know how much this person weighs in kilograms, not in pounds. And to do that, we look up a number, a conversion factor, and we see that there are 2.2 pounds per kilogram in 1 kilogram. So if we want to set up a similar problem to what we did before, we can do that with this new conversion factor, or this new identity. And we can say 155 pounds multiplied by this factor. Now, which are we going to put on the top and which are we going to put on the bottom? Right, so pounds on the bottom, because we want that one to cancel, kilograms on top. And then we put the numbers where they line up. So that's 2.20 pounds, 1 kilogram. Now when we go to solve this, because the 2.2 is on the bottom, we divide 155 by 2.2 rather than multiply it. And I think you come up with something like 70.4 kilograms. So again, our pounds have canceled, and we're ending up with kilograms. You see how that works? The biggest mistake that people make in these kinds of conversions is putting the wrong number on the top or the bottom.
Yeah.
You know, flipping it, multiplying instead of dividing, that kind of stuff. Is that?
That happens to me.
Yeah, and that's the most common thing. So the way to avoid that is to do the units first and then fill in the numbers later. So set up your problem the way we just did it, pounds, and then we say, okay, where do we want which units? We want pounds in the bottom so they cancel. We want kilograms in the top. Then we put the numbers in. That way, it gives you kind of an extra check against putting the number in the wrong spot. So let's try one that's a little bit trickier and see how it goes. So in this case, we're looking at a dialysis unit of water to go through. In fact, we need 75,000 milliliters of distilled water. So we're setting up our machine. We see we need 75,000 milliliters. We go to the store to get some distilled water, and we find big gallon jugs of distilled water. So we need to know how many gallons is 75,000 milliliters. Now once again, we're moving between the English system and the metric system. So we need a conversion factor, and it would be really nice if we had a milliliters per gallon conversion factor, right? Let's say we don't have that. Instead, we have a conversion factor that tells you 1 quart is 946 milliliters. So that's our English to metric conversion, 1 quart, 946 milliliters. What do we do with that?
There's ways to convert one part of it and then use the answer to that to convert it into.
Yeah, we're going to have to do a couple steps here. What does the quart help us? Yeah, because we can also look up or know that there are 4 quarts in 1 gallon. So we're going to have to go milliliters to quarts and then quarts to gallons. And the nice thing about this system with the unit cancellation is you can actually set it all up in one big line and then do the calculation all together. So see if you can set that up. I'll give you a couple minutes to work on it. And we'll see what everybody comes up with. All right, what'd you come up with? Let's hear some numbers. Anybody who got all the way through it? Yeah.
But 19.82 on gallons.
All right, what'd you come up with?
Yeah, I gotta go 19.9.
Okay. Anybody else? Anybody get something different? Yeah. Okay. Anything else? Okay, all right. Well, let's set it up and see what we get. So we're going to start with our given number. 75,000 milliliters. And then, so that we don't get messed up with these multiplying versus dividing, we're going to do the units first. What's our first conversion here? Quart. So that means we want quart on the top, because that's what we want, and milliliter on the bottom, right? Okay. Now we set the numbers in there. 946 and 1. So now we've canceled milliliters and we're left with quarts. What's next then? Quarts to gallons. So we want quarts on the bottom and gallons on the top. And the 4 goes with the quarts and the 1 goes with the gallon. Now we've canceled quarts and we're left with gallons, so we're good. The way that we calculate this then is to take 75,000, divide by 946, because that's on the bottom, and then divide again by 4. And I think that if you do that, you get one of these numbers just depending on rounding error. So I think it comes out to about 19.8 gallons. Great. Yeah.
I didn't do all those steps.
Okay.
I just did 75,000 divided by 3,784.
So you multiplied this times 4 first, and then divided by that number.
Yeah.
Yeah.
I feel like if I write all that out,
Yeah.
I might get confused.
Okay. She's saying that she multiplied this number by this number first, so kind of like multiplying these two together, and then divided this by that whole thing. That's fine. Multiplication is what we call associative, so it doesn't matter what order you multiply things in first, and yeah, that works too.
So it doesn't matter how you get the answer as long as you get the answer.
As long as you get the answer. Now this setup, setting it up like this can be useful when you have a really long, complicated conversion with lots of different steps. The simpler they get, the more you can take shortcuts. Like some people will tell me in this one up here, if you're going from milligrams to grams, well, you can just move the decimal place over by 3. And yeah, absolutely you can. And so, as I said, if you have these kinds of tricks, if you've had some experience with this, you have a good way of doing this, just stick with that. If it works, great. There's no reason you have to do it the way I'm saying that to do it. But if this is something that you've struggled with, or you prefer a clear step-by-step approach that will always work, this is one way that you can do it. All right.
Rounded it to 20 gallons, is that, or should I
Yeah.
safer to stick to the 19.8?
Good question. There are official rules about rounding and when you're supposed to round and not, based on the significant figures. Depending on how many significant figures you start with, then you use that to figure it out. There's a section in your book about it. I think it's 2.3. We're not doing that in this class. So our general rule of thumb is keep about the same number of significant figures as what you start with. So 2 or 3 in this case would be fine. So if you said 20 or if you said 19.8, that's fine. If you do a calculation and it comes out on your calculator with 20 decimal places, don't write them all down. Just cut it off somewhere about where the other numbers in the problems are, and we'll be good. If you're curious about how to really do it properly, we can talk about that, and I'd be happy to show you. It's not hard, it's just some more stuff to remember. But we're not going to be strict about that in this class. A good question. Does that make sense? Yeah. All right, let's try another one. Let's get a little bit trickier. Not trickier, just a little more to do. Same idea. This time we're going to talk about amoxicillin and antibiotics. Anybody ever taken that?
Yeah.
Not yet. You don't have to report your medical history, but it's common. Yeah, I certainly have. So a typical dose of that is 4 tablets per day. For 10 days. When you take antibiotics, you always have to take the full amount. Make sure you take all the pills, otherwise you're potentially increasing antibiotic-resistant bacteria. And in this case, we're going to say that each tablet was a 250 milligram tablet. All right, straightforward so far. 250 milligrams a tablet, 4 tablets a day, 10 days. So over this entire treatment period, the question is, how many ounces were taken? And then to make it a little more fun, we're going to use the same conversion factor that we used earlier, that 1 kilogram is 2.2 pounds. And then if you don't know, also there are 16 ounces in 1 pound. So you're given a number in milligrams, which you have to do some multiplication to get that full dose. And then you have to convert it to ounces. But the only conversion factor that you have between the English and metric system is kilograms and pounds. So what I would do in this case, and what I think you should do, is set up a little plan for yourself of how the conversion is going to go. I'm going to start with this unit, then go to this one, then go to this one, then go to this one, however many times you need to do it. Then set up the actual multiplication and see what you get. Give it a try. You don't have to work alone. Talk to each other. See what you come up with. Give you a few minutes to work it out. No, because milligram is 1,000, so there are 1,000 milligrams of gram and 1,000 grams of kilogram. There's 1,000 times 1,000 milligrams. So you're going to do probably more factors there. Those of you who are just kind of stuck, those of you who are getting started, how did you start this out? Okay, so you found the whole total dose, and that's there's a couple ways to do this. You could convert the 250 first, and then multiply by the 4 and 10, or you could do that part first, get the total dose, and convert that to ounces. So if you multiply 250 by 4 by 10, you get the total dose, what do you get?
10,000.
10,000. So take that in milligrams then and start trying to do that conversion.
But you can't go from milligrams to
I mean, you can if you know the number, but if you don't know, you should go milligrams to grams and then to kilograms. It's not. How many milligrams are in a gram? How many? Anybody know? How many milligrams are in a gram? 1,000. So there are 1,000 milligrams per gram, and then 1,000 grams per kilogram. If you are getting through this and you think you got an answer, I hear some talking. That's great. Talk about it. See if you can figure out what you did differently from somebody else. Taking a couple more minutes to look at it, talk about it. All right. So what kind of numbers did you get? 0.325 ounces? 352? What do you think? It's different? Same? That's what you got? Anybody get something different?
Yeah, I guess I'm taking like
3? Like 3 ounces? Okay. Anything else? No? Have you got anything else but these? You just don't want to say? You could be wrong. There's no like penalty for being wrong. It's fine. Still figuring? Okay. All right. Well, let's kind of set this up and see what it looks like, and what it looks like compared to how you set it up. So we start with this 10,000 milligrams from the total dose, multiplying all that stuff together. And we have to kind of come up with a conversion plan here because we don't have a nice milligrams to ounces conversion here. So we're going to go, we want to get to kilograms, because then we can convert to pounds, and we know we can get pounds to ounces. So that means we've got to go milligrams to grams, then grams to kilograms, because we know those are 1,000 each. Then we can go to pounds, and then we can go to ounces. So that's what our conversion will look like. Milligrams to grams, grams to kilograms, kilograms to pounds, pounds to ounces. Now it's a matter of setting up all the fractions with the units in the right place and then plugging in the numbers. So milligrams to grams means milligrams cancel and we're left with grams, right? Then grams to kilograms means we want grams to cancel and kilograms to be left. Kilograms to pounds. And pounds to ounces. And that should take us all the way. Now we just plug in the numbers. So how many grams in a milligram or how many milligrams in a gram? Yeah, we've got 1,000 milligrams in a gram. Then we've got 1,000 grams in a kilogram. Then our conversion factor here tells us that there are 2.2 pounds in a kilogram. And there are 16 ounces in a pound. So that means to solve this, we should take 10,000, divide by 1,000, divide by 1,000 again, multiply by 2.2, multiply by 16. So I think if you go through all that, you get 0.352. So if you got 3 or you got 35 or 350, something like that, chances are you forgot one of these zeros here, forgot to divide by something, or hit 100 instead of 1,000 on your calculator.
Did you go through the actual multiplication? How you cancel that?
Yeah, so we're going to say 10,000 divided by 1,000, divided by 1,000, multiplied by 2.2, multiplied by 16. The milligrams cancel here, grams cancel here, kilograms, kilograms, pounds, pounds, and we're left with ounces. Okay, so sometimes they get big, but the procedure, the technique is still the same. You set it up, you cancel the units you don't want, you keep the units you do want, and then you've got your answer. Okay. So let's throw one more thing in there, and that is density. What is density? How thick it is? Okay. How much weight is in it? Yeah.
How much mass something has for its volume?
How much mass something is for its volume? Yeah. Yeah, it's a measure of how much stuff is in a given amount of space. So how much mass in a given amount of volume. Volume tells us a space, an amount of space. And then the mass of stuff inside that space is the density of that object. So we can think of it as the mass in a given volume, or more generally as amount of stuff in a given amount of space. So something that is more dense will have more mass for the same amount of space. So what's an example of something that is very dense you know about? Black holes, yes. Black holes are incredibly, incredibly, incredibly dense. The densest things in the universe, I think. Yeah. What else is dense? Water? Sure, compared to some things, yeah. What's more dense than water? Metal? Some metals, yeah. How would you know if a metal is more dense than water? If it sinks, yeah. If you put it in water and it sinks. So are ice cubes more dense than water?
Yeah.
Yes? No?
Equal?
Equal? They float? Yeah, actually they float, right? But they don't kind of get up on top of the water. They sort of are mostly in the water with a tiny bit peeking out maybe in the top. So that means they're a little bit less dense than water, but not a whole lot. So what is the, and we'll look at a picture of that, what is the measurement of density? Anybody know? Standard units of density? I don't know if everybody's ever seen this, but it is grams per milliliter, or grams per milliliter is another way to write that. Could write it as a fraction as grams divided by milliliters. Another way to write that you also might see is grams per cubic centimeter. If you imagine a little cube that is a centimeter on each side, that is exactly 1 milliliter. So a milliliter and a cubic centimeter are the same amount of volume. So you may see that both ways. What is the density of water? Any ideas? No? Nobody heard this? Okay. Well, now you know. Water, well, not yet, but you will know in like a second. The density of water is 1 gram per milliliter, or it's about 1. It depends a little bit on temperature. If it's, but it's always really close to 1, like 0.999 something or 1.00 something. It's about 1. So anything that's more dense than water, sinks in water, has a density of greater than 1. Floats, it has a density of less than 1. Now, we have to be a little bit careful of that because there's also issues of buoyancy. Like a boat can be more dense, but because of how it's shaped, you have these other forces. So the sinking thing is not always right. But in general, we can say if we have a particular bulk sample of material, that this will be the case. So here's a picture and a little table to help us talk about density a little bit. This is from the book. So you see here a picture of a beaker of water, and there's some stuff in it. You got a cork, an ice cube, some aluminum, and some lead. The cork has a much, much lower density than water, and so you see it kind of floats out of the water, really, mostly out of the water. The ice, the density is just a little bit less than water, so it floats to the top with a tiny bit peeking out. Then you've got your water, density of 1. The aluminum and the lead both sink because of their greater density. And you can see in this table some common substances. So you have some really light solids like cork and wood that will float. You have some heavy solids. There are light liquids and heavy liquids. Generally, as you dissolve more stuff into water, it becomes more dense. So that's why bodily fluids and syrups and that kind of thing become more dense. And then gases can have density too, although a lot of gases are much, much, much less dense than water. All gases are much, much less dense. Our units have changed completely. So instead of grams per milliliter, we're now looking at grams per liter. So 1,000 times less dense than anything on the liquid or solid scale. Also note here that oils are slightly less dense than water. So if you pour oil on water, it will sit and float on top. You may see that, like if some oil's in a puddle or something, it kind of floats on top and makes the rainbow colors. That's the reason I point that out is that people often think that oil is heavier than water because of its viscosity. It flows very slowly, you know, it kind of takes its time to get around. But it's actually less dense than water. It will stay on top of water. So that's density. Now let's, with our last little bit of time here, let's look at how density can fit into some of these conversion problems. What density allows us to do is relate a mass with a volume. And that's really powerful because all the conversions we've done so far we've taken a mass and just turned it into a different kind of a mass, like a kilogram and an ounce or something like that. Or we've turned, or we can turn meters into feet or that kind of thing, staying within the same type of measurement. Density allows us to change our type of measurement, to take a mass, grams, and turn it into a volume, milliliters. This is enormously helpful in a lab type environment because a lot of things are more easily measured either on the balance or by volume, and this allows you to actually do that. So let's practice that. Let's say we got some cough syrup. 2 teaspoons of cough syrup. Anybody ever had cough syrup before? Kind of yummy. Makes you stop coughing. You can hallucinate if you drink a bunch of it. And let's say that the cough syrup, would you say it has a high density or a low density? Probably. Yeah, it's pretty dense. And that's part of how it works, is it kind of coats your throat to settle things down. In fact, in some studies, one of the common cough syrups really had no particular advantage over honey, because they found that the reason the cough syrup worked was that it just coated your throat and stopped the coughing. It wasn't actually the medicine in that it really did anything. So density of cough syrup is pretty high, 1.2 grams per milliliter. So the question is then, what is the mass of these 2 teaspoons of cough syrup? And you need to know one more piece of information, and that is that there are 5 milliliters in 1 teaspoon. So we set this up just like a conversion problem, but we need the density to get us from volume to mass. So what we do, so we say our basic plan here is to go from teaspoons to milliliters, and then use the density to get from milliliters to grams. Normally, there isn't just some standard conversion factor that gets you from milliliters to grams, but each density of each type of thing will get you there. You can use that if you know the density. And next week in lab, we're going to measure some densities and use some densities, so we'll get a little bit more practice with that. So we've got 2 teaspoons times, and what are we going to put on top and bottom here? Yeah, milliliters on top and teaspoons on bottom, because we want to get rid of the teaspoons and end up with the milliliters. So we've got 5 milliliters per teaspoon. And then the last part is to get from milliliters to grams, and we do that using the density. So we've got 1.2 grams per milliliter. That's the same as writing 1.2 grams per 1 milliliter. So that's how our conversion factor looks in an equation like this. 1.2, that's what we're told, that's what the density tells us. It's not a standard conversion factor. We can't just say there are always 1.2 grams per milliliter. It depends on the substance. Because it's this cough syrup with a density of 1.2, we say 1.2 there. If there were water, we'd put a 1 there. It would be 1 over 1. All right, so we multiply that out. It should come up to about 12, right? 12.0 grams. And that's the mass of the cough syrup. Okay, here's one for you to try, a little bit different. Let's say we have a glucose solution. Glucose solution can be given intravenously if someone's low on glucose or can't eat for some reason. And this glucose solution has a density of 1.15 grams per milliliter. Question is, how many liters are 575 grams of this glucose solution? So we're given a massive glucose solution. We want a volume in liters. Think about the density. Think about how you can take a plan of conversion and make that happen. Give you a couple minutes and then we'll talk about it, and that'll be it. All right, we only got a few minutes to go, so we'll. How did this go? You got what? 0.5 liters. Okay. Anybody get something else? How'd you set this one up? You want to volunteer?
I did 575 grams times 1.
All right, so hold on a second. So in this case, you want to go grams to milliliters, right? And then we want to get rid of milliliters and end up with liters. So we use those same numbers, but we have to make sure that the number goes with the correct unit. In terms of the density, it's 1.15 grams per milliliter, not milliliters per gram. So we have to make sure that the 1.15 goes on the bottom and 1 goes on the top. And then here we know that there are 1,000 milliliters in 1 liter. Okay, we multiply all that out, and I think you get something like 0.5 liters. Yeah? Yeah, I just kept the 3 significant figures because that's what we started with, but again, not a big deal. Okay. All right, so I'm sorry that this chapter is a little bit dry and we don't really get to talk about exciting things, but this is a really, really crucial skill for this class. We're going to use this in pretty much every chapter in one form or another. In the next chapter, we're going to convert energies, then we're going to convert moles and chemical reaction stuff. We're going to keep using this over and over again, so please practice, please make sure you got it. Our first quiz will be next Thursday, so a week from today, at the beginning of class, on this kind of stuff. So for Tuesday, make sure you have your lab report and pre-lab from lab 1 and your pre-lab for lab 2 done, so you can come in and do the lab. And make sure you're dressed appropriately for lab as well. What? A week from today, it will be the quiz, yeah. All this stuff, chapter 1, or chapter 2, whatever it is, the measurements chapter, the first, yeah. Check the calendar, they'll always be during the lab. So we'll meet down here and have regular class first, and then we'll go do the exam.